Hello, I'm the awesome Tutor, and today we're going to be looking at nuclear fission and nuclear fusion. So, nuclear fission. Nuclear fission is the splitting of larger parent nuclei into smaller daughter nuclei. So, large nuclei into smaller nuclei. And it is not the splitting of an atom. No, that will not get you a mark in the exam. It is the splitting of nuclei, which is the plural of nucleus. It involves an isotope which is struck by a neutron, and this isotope absorbs the neutron and therefore becomes unstable and splits apart, releasing large amounts of energy which was stored in the nucleus. So nuclear fission is a way to release this energy. Now, the fission fuel. First of all, fission is not a natural event. We do it, okay? We make nuclear fission. Isotopes that are used as a fuel in nuclear fission reactors are uranium-235, which is a specific isotope of uranium, and plutonium-239, which is another specific isotope of plutonium. Now, uranium-238 is more common, but does not undergo nuclear fission, so we can't use it. And only 0.7% of natural uranium is 235, which does undergo nuclear fission. So we have a problem here. So what we do is, before the uranium can be used as a fuel, uranium needs to be enriched. And this is a good term to use in your exam. It needs to be enriched until it has 3% uranium-235, which can undergo nuclear fission. So we have to enrich the uranium so there's more uranium-235, which can undergo nuclear fission. This is a reaction. So as I said, the isotope is struck by a neutron, and it absorbs this neutron, because now it's 236, not 235, and becomes stable. And so the nucleus splits into two. In this case, it's krypton and barium, but it's not always krypton-barium. Sometimes it's, say, strontium-90 or xenon-1444. So xenon-144. And obviously, a large amount of energy is produced. Now, in your exam, if you're asked to draw a diagram, you don't have to state the names of the substances produced. You can just draw circles representing them. And here's an important thing you need to know. These neutrons which are produced, so nuclear fission produces 2 to 3 neutrons, because the amount of neutrons and protons here is equal to the amount of neutrons and protons here, so it's conserved. And these 2 to 3 neutrons produced, they cause something that is called a chain reaction, as shown here. They collide with more uranium isotopes, and they cause more fission reactions, which in turn create even more neutrons for more fission reactions. So it's like an exponential reaction. It increases by more and more and more each time. So it involves fast-moving neutrons from the nuclear fission reactions, 2 to 3 produced, and they collide with more uranium nuclei and more fission reactions. Here we have a nuclear reactor. Now, the yellow things are called the fuel rods, and they contain the enriched uranium or the plutonium-239, and this is the fuel. They are surrounded by coolant, or a moderator, which circulates the heat produced from the nuclear fission reaction. And here we have the black things, which are control rods made of boron or cadmium, which absorb neutrons without undergoing nuclear fission. So they essentially reduce the amount of neutrons produced. They reduce the chain reactions. They slow down the chain reactions, and they can be lifted in and out. If they're lifted out, then the neutrons produced can trigger chain reactions. If they're lifted in, the chain reactions are slowed down. So this allows us to control the activity of the nuclear reactor. And then heat from the fission is spread out through the coolant to the heat exchanger here, which contains water. And then we go to the generic process of producing electricity. The water evaporates into steam, which spins a turbine, which turns a generator, generating electricity. Now, nuclear fusion. Nuclear fusion is a process that powers the stars. And so it is a natural event. And it's mainly in the main sequence of the stars. And involves small nuclei joining together to form larger nuclei. So nuclear fission was the splitting of nuclei. Nuclear fusion is the fusing of nuclei. And nuclear fusion releases a large amount of energy, just like nuclear fission. And for nuclear fusion to occur, we need the Goldilocks conditions. High temperature, high pressure, like those found in stars, to overcome the repulsive forces of the nuclei, so then they can fuse. And so therefore, scientists have found it difficult to create the extreme conditions needed to carry out nuclear fusion on Earth. So we don't have nuclear fusion reactors, they are only experimental up to this point. Here we have the reaction. Now deuterium, which is an isotope of hydrogen, where its mass number is 2. Tritium, which is an isotope of hydrogen again, where its mass number is 3. You don't need to know the reactants or the products produced, but you do need to know that it involves the fusing of nuclei. And maybe helium is also produced. So the deuterium and the tritium, they join together and they fuse. And then helium is produced and also a neutron, and definitely, obviously, energy is produced. Now nuclear fission versus nuclear fusion. Nuclear fission uses non-renewable fuel. Uranium will run out. Nuclear fusion is essentially renewable because hydrogen can be extracted from seawater, and so it's essentially unlimited. Uranium ores are common, and they will last us decades, but they will eventually run out. Hydrogen can be extracted from seawater, and so it's essentially unlimited. Nuclear fission is expensive, especially if you're going to set up a nuclear fission reactor or decommission it, dismantle it. Nuclear fusion is cheap once it's been implemented. But right now, the research going into it is more expensive, and some feel that the money can be used for better things like researching into renewable energy, like solar power. Now, nuclear fission, it produces a lot of radioactive waste, which must be safely stored for thousands of years. For nuclear fusion, it also produces radioactive waste, but it decays in a very short term compared to nuclear fission and produces a small amount compared to nuclear fission. Both of them, no greenhouse gas emissions, no CO2, so no contribution to climate change, and no contribution to global warming. And both of them produce a high amount of energy. This has been the Awesome Tutor. Bye!